All right. So I just sent the URL of tonight's live stream. So for people who want to get the live stream, URL, this is it. So with that, I'm going to get the class started. So a few things to do. The first one is to kind of go over part 1 at least. I think we can go over part 2 too, but I have to look at the due date because sometimes I say that at the wrong time, like 10 p.m. Then I cannot talk about it yet, okay? Because it's people can still work on it. But part 1 is definitely past due at this point, so I can talk about it. All right. So do you guys want to talk about part 1 of the carry look ahead lab, or is everything kind of okay with that lab and there's no need to talk about it? We all good? I'm getting confirmation that we are all good. So, all right. Okay. So, okay. Remember this one? You have to kind of look at the gates and find out which one is P, which one is G, and which one is Q. And that all has to do with the definitions of P, G, and Q, how those are defined in my notes. Okay. And then we have to look into kind of what goes in here. This is K1, okay, because the text says this is actually a mistake. It's K1, and then we have to figure out how to get to K1 using P, G, and K0 as input pins. Now the most important part is P and G are 3-bit pins, so you have to break them apart first. Okay, can I answer your question? Is there a question for me? Nope? Okay. So because P and G are 3-bit pins, you cannot just take the entire thing. You have to break it apart using a splitter, get P0 and G0 out of those 2 multi-bit pins, and then use an AND gate first, and then use an OR gate as the second gate, and then the output becomes K1. So are there any questions about this part? Okay, no questions. And I think that's kind of the end of the first lab. And you basically have to work on K2 and K3 as well. They are just more complicated versions of K1. All 3 were defined in the notes. Okay, the way they are expressed as a whole bunch of ANDs, and then and then an OR to take all the results of AND, as the final result of the carry bit. Those are all in the notes. Okay, so basically it's really just a motivation for people to read the notes and understand the concepts. So do we have any questions about this lab? No questions? All right, we're going to move on. So moving on, we are going to talk about binary number comparison. We are done talking about subtraction, so we are now moving on to talk about comparison. So comparison is kind of a big topic, because a lot of C code, whenever you need to make a decision, should I go for another iteration? Should I go to the then statement, or should I go to the else statement? A lot of times when you need to make a decision, it's all based on, those are all based on conditions. Conditions eventually boil down to Boolean operators, and or not. But they are only applied to other Boolean expressions. So when you boil down everything, a lot of times, most of the time, it boils down to comparison. Okay, we are looking at a value, and we are trying to see if it is less than, greater than, less than or equal to, greater than or equal to, or not equal to another value. Okay, is that okay so far? Okay. So the first part of this note is really just to illustrate how we can use just less than combined with other Boolean operators. Then we don't need greater than, we don't need less than or equal to, we don't need greater than or equal to, we don't need not equal to, and we do not need equal to. We just need to know whether something is less than something else. That's all we need. So that's what this part is about. Okay? So assuming that you only have a single comparison operator, less than, but you have not, you have and you have or, how can we implement all of the other comparison operators using only less than? That's what this part is talking about. If you want to implement greater than and all you have is less than, that's pretty easy. You just switch the 2 sides so that to confirm that x is greater than y is really the same thing as to confirm y is less than x. So that one is pretty easy to do. You just have to change the expressions on the 2 sides of the comparison operator, and you're done. x is less than or equal to y. Well, in that case, it is the same thing as saying it is not the case that y is less than x. Is that okay? Does everybody understand that if you want to say that x is less than or equal to y, it really is saying the same thing as it is not the case that y is less than x. Does that make sense kind of intuitively? Okay, good. So x is greater than or equal to y. Just switch the operands and you have it. Okay, let me move the cursor away so you can see the actual comparison. Okay. And then we have x does not equal to y. Well, x does not equal to y is actually pretty easy too, because all you have to say is to say, well, x does not equal to y means the same thing as x is less than y or y is less than x. Does that make sense? Okay. And then the last one is x does equal to y. Well, since we already know how to express x does not equal to y, x does equal to y is the negation of that. So I just kind of took the easy way out and say that it just take the negation of the previous one. So do we have any questions of how we can use only less than and the Boolean operator or logical operators in order to implement all of the other comparison operators that we are familiar with? Are we good? Okay. So this is kind of interesting, along the same line as NaN2 can be used to replicate all of the other logical operations that we are familiar with. Do you guys remember how NaN2 can be used to make negation, disjunction, and conjunction? Well, likewise, we can use only less than to implement all of the other comparison operators. So that's all we need to do for now. Okay? We just want to know how do we confirm a value x is less than a value y. So we're only focusing on can we confirm less than. Is that okay? So that's kind of the premise for the entire module, is to say, okay, we just want to know is x less than y. Are we doing okay so far? Okay? Yep.
Can I just ask about where it says x equal y?
Mm-hmm.
Why is it not the negation of and? Because if it's equal, wouldn't it be true that x is less than y, or not, x is not less than y and y is not less than x?
Okay, so can we agree about the not equal to?
Yeah.
So if x does not equal to y, is really the same thing or is equivalent to x is less than y or y is less than x, to confirm that x does equal to y is to negate whatever we had before. So putting this negation here and put everything else inside the parentheses is the quickest way to do it. Now, if you want to simplify this using Demorgan's law, okay, then it becomes the negation of x is less than y and the negation of y is less than x. So you're basically saying if x is not less than y and y is not less than x, then x and y must be the same thing. So that works too. But that's because Demorgan's law can be applied in this case. Because you have a negation on the outside, the negation is applied to the result of a disjunction. So you can apply Demorgan's law and quote unquote simplify that to what you just said. But this is equivalent to that as well. It's just that I was lazy and just say, okay, if this is saying not equal to, I just negate it and it becomes equal to. So are there any questions about these? Nope. Okay. All right. So the first thing we want to do is to talk about unsigned comparison. Okay. And on my way walking over here, I think I have a better way to explain this, but we're going to stick with the notes a little bit, and then we'll digress from the notes a little bit as well, because I think I have a better way to explain all of this. So the later part, we can digress a little bit from here. Okay, so the first thing has to do with what is the value represented by a bit pattern when we choose to look at the unsigned interpretation of a bit pattern. Okay, so that's the first question. Okay, we want to answer that question first. So to answer that question, I am going to use an equation And hopefully you guys remember that, because we talk about this when we talk about base conversion and different bases. So let's see if you guys can still remember this stuff from a few weeks ago. All right, so I think this will work. There we go. All right, so we're going to say the value of a certain bit pattern x is some summation. So in this case, we'll say n minus 1, excuse me, n is the number of bits. So with most of the examples that I do in this class, n equals to 3 or n equals to 4, because we are talking about 3 or 4 bit patterns. Realistically, in a computer, a byte means n equals to 8. And on a 32-bit platform, n usually equals to 32. And on the 64-bit platform, n usually equals to 64. So, but I'm just saying n, okay? X is an n-bit pattern. So the value being represented by x, which I use v of x to denote, is basically just taking a look at each digit. So d of I is digit I. And we multiply that by the base, which is 2 in this case, raised to the power of I, which is the position of the bit. Have we seen this before? Okay, excellent. If you're nodding your head or you vaguely recall something like this, that's good. If you're saying, I have never seen this before, you probably need to review the material, because we have talked about this before, and it is important to retain information or knowledge from earlier lectures, because everything built upon earlier concepts. Okay, so we kind of know this already, and this is the unsigned interpretation. All right, so to compare two unsigned thing is really to say, okay, we look at the summation of I equals 0 to n minus 1 di. Okay, excuse me, I shouldn't be using di. I will be using xi, because xi is from x, and we want to see if it is less than y, and the value represented by y is kind of the same kind of equation, except we use xi to represent bit I of the bit pattern y. Okay, are we doing okay so far? All right. So now the question is, how do we do this? Okay, do we have something when we talked about subtraction that is already telling us whether x is less than y already? Yes?
This was our, not the export, the other one we used when we were determining, what's the word, not carry, the opposite carry.
Borrow. Yes.
Borrow.
Yes. So the borrow flag gets the job done. So but we want to ask the question why. Why does it get the job done? Okay, because if you read other textbooks, okay, if you read textbooks or even data sheets, does everybody understand what is a data sheet in industry? So if you work with electronics like microcontroller units or some other chips, the data sheet is basically sometimes really long, like 300 or 400 pages long. It's a document that tells you about how a particular chip functions. Okay, so if you read that type of documentation, it's not even a textbook. They will tell you that if the carry flag or the borrow flag after a subtraction is a 1, that means the minuend is less than the subtrahend from the perspective of looking at those bit patterns as unsigned values. Okay, so the knowledge is there. The question is, why? Why does it work? Okay, because I want to know why it works. Okay, so the first thing we want to do is to say, if you have 2 bit patterns, okay, I'm going to give you a concrete example here, and then we'll move it into a kind of more abstract discussion. So we'll start with, I don't know, maybe 0, 1, 0, 1, and I ask you, is it less than 1, 0, 0, 1? And here's a question mark, because I want you to tell me, is it less than? And remember, I want to look at these bit patterns as, I want to interpret the bit patterns as unsigned values. Okay, so throw all the signed interpretation away for now, and we just want to look at the unsigned interpretation. So do you need to look at the actual value, or do you have a faster trick and say, okay, I know which one is, whether it's less than or not? Yes?
So faster trick, you start from the leftmost digit and check, okay, is the one on the left 0 compared to the one on the right being 1? If so, it's less than. Otherwise, go to the next bit.
Okay, so you look at this x here, and you say this, you look at a 0, you look at a 1, and because 0 is less than 1 as the most significant bit, you can conclusively now say, x, which is the one on the left-hand side, is less than y, which is the one to the right-hand side. Right?
It has to be 0 and 1. Matched pairs don't tell you anything, so you have to move to the next bit. And if you've got a 1 on the x and 0 on the y, then you know that the answer would be false if you reached a bit where that's true. But you'll only reach a bit where that's true if all bits before it are matched pairs.
Okay.
Or doing this.
But why does it work? So this is the question. If you don't look at the less significant bits, okay, these 3 on x and these 3 on y, what makes you think that 0, 1, 1, 1 for x is going to be less than 1, 0, 0, 0? Yes?
So it's because each place
Uh-huh.
has a certain value.
Yes.
So you've got 2 to the whatever.
But when you're
that place. If you were to ever reach the value of the next place, the only way you can do that is by having a 1 in that place and at least a 0 in all the other places. So if you're going to have, if you've got a 0, let's say you've got a 0 in the third place. Then there, and you don't have, and the bits before that, and the bits to the left of that don't matter because because it's either it's the most significant bit or we've already checked those. Then we know that the remaining significant data cannot possibly be greater. It cannot possibly be equal to or greater than 2 to the 3 that we said in third place.
Okay. So what I'm hearing you say is if you sum, from I going from 0 to, I don't know, let's just call k here, okay? And this time we confirmed that each one is there, okay? So we have 2 to the power of I. You're saying that this is always going to be less than 2 to the power of k plus 1.
Yes.
Why?
Is it because the most significant bit, the value in it, is always going to be bigger than all the values before it combined?
No, it's only the way we interpret the digits is digit I represents how many base to the power of I we have in the value. But we never really stated or confirmed that if you take one single digit out of digit k plus 1, okay, if that is a 1, then the value being represented is going to be greater than all of the other less significant bits added together. Yes?
Because you've got base to the power, right?
Yes.
The base to the power is so you've got a lower power.
A summation of all the lower powers. Yes.
You're never going to equal that power because otherwise you would have that power.
Okay, that's kind of circular in a way. I think you understand the concept intuitively.
Having trouble articulating.
Yes. Okay. And that's why we like math. Yes.
Well, each bit is 1 plus the sum of the maximum value of all the preceding bits.
Okay, so now we have a chicken and egg problem because, how do you confirm that too, right? So here is my explanation. So if I can go back to my notes here. Okay, so how do we prove just that? Okay, which is the same thing that I have presented you a little bit earlier, except this time I use n and not k. Okay, so the question is, how do we know that 2 to the power of n is greater than the summation of all the bits that are less significant to n? In other words, how do I know that 2 to the power of 4 is greater than 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3? Now, you can say 1 plus 2 plus 4 plus 8 is what? 15, right? 2 to the power of 4 is 16, so we can confirm that one instance. when n equals to 4. But how do we prove it in general? So go ahead and then we'll get back to you. Yep.
Can't we say that it's because it's the leading digit?
Nope. Because the leading digit, all it's saying is digit 4 is representing the quantity of 2 to the power of 4. That's all it's saying. That's how it is defined. So whether one single 2 to the power of 4 is greater than the sum of all the earlier digits of all the less power of 2's, that remains to be proven. Go ahead. Yep. Okay, that's fine. All right, no problem. So we just want to look at this because this is how I function. Okay, I look at something simple and go like, well, it looks like it is true. I can use a whole lot of examples to show that it is true, but can I prove that this is true? And can I prove it to myself conclusively that this is true? So, so the proof goes like here. So from here to here, this is the actual proof of that particular theorem. The theorem is just this part here. Okay, if you look at this part, this is the theorem, and this part here is the proof of that theorem. And somebody who has taken CISP310 will say, but this is not 440. We are not supposed to be proving in this class. Well, you're probably right about we are not supposed to be proving here. But when I write something down, I need to know that it is true. Okay? So for those of you who have taken 440, CISP310 discrete structure, you might recognize this. It is called proof by induction. Okay? I'm not going to go through the details of proof by induction. So for those of you who are curious and want to understand what is proof by induction, you might want to read the details a little bit more. Okay? But the conclusion is, this is actually true. Okay? That statement is true. All right, so if that statement is true, how is it going to help me understand that the overall borrow of a subtraction, binary subtraction, is all we need to confirm whether the minuend, which we call x, is less than the subtrahend, which is what we call y, when we name the rows. Okay, so let me present that kind of using here. And we ask, so let's say B is the overall borrow. Okay, this is the overall borrow. So now the question is, B is 1 if and only if x is less than y. Or I should say the value represented by x is less than the value represented by y unsigned. And I want to know why, okay? Is it always the case? Does it only work sometimes? Can I mathematically prove that this works all the time? Is that okay? Are we doing okay or not? Does everybody understand what I'm trying to accomplish? Okay. So let's assume we have n bits. So the minuend has n bits, the subtrahend has n bits, the difference has n bits. Okay? So the overall borrow is actually Bn. That's how we label the various bits. Okay? Bn is the overall borrow bit when we have n bit minuend, subtrahend, and difference. Is that okay? Can someone help me? In my usual text, I use T of n to represent this bit. How is it defined? I think by now we probably should remember that. How do we define a certain borrow bit, which I use T for take, right? So how do we define T of I plus 1? Does anyone remember? Yes, we only look at the x and y and then also the q and the t, right? So what is the equation? The borrow? Okay, and then there's an or, right?
Yeah, and the or, and then it's viral, this is going to be q n minus 1 and t n minus 1.
Yep, that is correct. Okay, so this is stuff that we have already talked about all the way back in binary subtraction. That is how we define a borrow bit, okay, or the take away bit. Is that okay? So now the question is, how can I use one single bit to tell whether the unsigned value represented by x is less than the unsigned value represented by y, and only using just the borrow bit, the overall borrow bit, which is tn in this case. Yep.
Is it because the process of determining the borrow value, it lets us know whether or not x is overall smaller than y?
It has to do with how we define borrow. And it has to do with how we define the take away bit by combining the two borrows. Okay, so it has to do with those. So whenever we have a question like this, and we can recall an expression, then the next step is to find out, okay, how did we exactly define b as a function? Okay, that would be the next step, because we need to look into that and find out, okay, does it tell us something about subtraction or comparison? So let's go ahead and define what is b. Okay, do you guys still remember what is b of something instead of c of something? It's the negation of x n minus 1 in this case, and y n minus 1. It's negating the first one and the second one non-negated. Is that okay? Now, if you look at this and go like, yep, I remember that, great. If you look at this and then say, I have no idea what b is, that means you need to review the notes a little bit, okay? So this is a good kind of, assessment, that is not graded, but at least you get a sense of, where you stand when it comes to the understanding of the material. Okay, I can do the same thing with q and t. Are we doing okay so far with this? Yeah, okay. So I look at this and say, well, this is an or, which means if at least one side is a 1, then we have a overall borrow of 1, right? Okay, so what does it mean when I have an overall borrow of 1? Well, we got two ways to make it true, okay? So we can say, well, what if this is a 1? If this expression is a 1, what is it telling me? What is it telling me about x subscript n minus 1? What is it telling me about y subscript n minus 1? Or can I just say that, hey, if this expression, if this conjunction is a 1, there's no way I can actually tell what is x n minus 1 or y n minus 1. Or is this sufficient to tell me exactly what those bits are? What do you think? Okay, because it's a conjunction. Yeah, go ahead.
If you get a 1 out, that means x is 0 and no. Yeah, x is 0 and y is 1.
Yes. Okay. So we are looking at the most significant bit of the minuend, which is x n minus 1, and the most significant bit of the subtrahend, which is y n minus 1. And we have now locked down, right? We have just locked down the actual value of the most significant bits. The most significant bit of x is a 0. The most significant bit of y is a 1. How does this relate to something that we talked about earlier, that whole thing about some theorem that I was trying to prove by induction? How does this relate to that discussion? What do you think? Okay, so we know that there are other bits of x, right? This is just the most significant bit. There are other bits of y. There are other bits of y. Just looking at the most significant bit, can I now confirm that x is less than y? The answer is yes. Okay, why? Because even if x has all the less significant bits being a 1, and even if y has all the less significant bits being zeros, the value represented by x can only be less than the value represented by y. Why is that the case? Well, it's the theorem that we have just proved. Okay, that theorem is the conclusion of saying, oh, by this, we already know that x is less than y. Okay. This implies x is less than y. Great.
So we're saying that if there's a one in the bottom,
Mm-hmm.
then the most significant bit of x has to be a 0. Is what we're
Yes. So this is only one part of the two-parter. Okay. So all I have proven at this point is if Tn is a 1, which is the overall borrow, right? Tn is the overall borrow. So if the overall borrow, and it is because of the first borrow expression, then we can tell and say that, okay, if that is the case, we know x is less than n because of the theorem that we talked about earlier. Okay? But unfortunately, this is not the only way to make Tn a 1. Because Tn can be a 1 because of the disjunction. It can be coming from the second part, right? So now we have to look at the second part and go like, okay, what if the second part is true? In other words, we look at this sub-expression, and then we say, okay, what if that is true? If that is true, what is that telling you? Using the same argument. Q n minus 1 is 0. Okay, this implies that Q n minus 1 is 0. And what else? Yep. So Tn minus 1 is a 1. Okay. I look at this and go like, what can we tell from here? Okay, what can I tell when Qn minus 1 is a 0? In other words, can I tell something about x and y if I just know that Qn minus 1 is a 0? What do you think? How is Q defined? It's an exclusive OR between the x and the y. Okay, so let's write it down. So we'll say Qn minus 1 is xn minus 1 exclusive OR yn minus 1. Okay? So if the exclusive OR between xn minus 1 and yn minus 1 is a 0, what does it tell me about those two bits? They are the same. Very good. Okay. So this implies that xn minus 1 does equal to yn minus 1. Okay? Well, if two bits are the same, in other words, if I look at the most significant bit of a number and they are the same, that alone doesn't tell me which number is smaller. Cannot confirm that the first one is less than the second one, does it? Right? Okay. But we have a second clue. The second clue is Tn minus 1 is 1. What does that mean? We apply the same equation, right? We look at Tn minus 1 and say, oh, that's the borrow of xn minus 2 and yn minus 2, or the borrow of Qn minus 2, comma Tn minus 2. Right? Then we reapply the same logic and say, oh, so that means if Tn minus 1 is 1, then either xn minus 2 is a 0 and yn minus 2 is a 1, which then conclusively says, okay, x really is less than y, or we push it back one step further, which means both the most two significant bits are the same, but the Tn minus 2 is a 1. Then we push the argument back one step further. So we can basically recursively apply this reasoning until we get down to x0, y0. Or until we find that they are different. But the conclusion is the borrow flag, the overall borrow flag, which I know here as T of n, is sufficient to tell us that the unsigned value represented by x is less than the unsigned value represented by y. Okay, so I'm just going to conclude here without going a little bit too much into this, and we just basically say if the borrow, okay, which is Tn, so I'm going to use both notations here. the overall borrow of a subtraction, which is also known as T of n for an n-bit subtraction, if this is 1, this is a 1 if and only if the unsigned value of x is less than the unsigned value of y. Are we okay so far? Do you think I really need to use if and only if, or do you think if is sufficient or only if is sufficient? Are there differences?
It would be necessary because isn't the notation for signed values much different?
Well, we kind of ignore signed values for the time being, okay? This is all about unsigned, okay? So the question is, if I change this double-sided arrow to a single-sided arrow, does it change the meaning? And if so, how does it change the meaning? Yep.
It definitely changes the meaning.
Yep.
But I'm unable to determine without further thinking whether or not it changes, or whether or not it changes, whether or not it's true.
Whether it applies here.
Or applies here, right?
Okay. So let's go ahead and look at this entire thing as one thing. Okay, we call this A. A. And then we look at this entire thing here, we call this B. Is that okay? So A is a Boolean thing, right? Because the most significant, the overall borrow is either 1 or it's not a 1. Right? So it's Boolean, it's true or false. We look at B, it is also just true or false. The unsigned value of x is less than the unsigned value of y, can be true or false. Right? So we want to know, the true false value of AB and how they correlate. Okay? So this is one of the things where you may not have learned it in your other classes, but I want to introduce you to this concept even though it is not the core concept of this class. So we got AB, we got A if and only if B, we have A implies B, and then we have A is implied by B. Okay, and we want to look at these and say, well, are they different? If so, how are they different? So we look at A, B, and go like, they can both be false. A can be false while B is true. A can be true while B is false. And then A can be true while B is true as well. So we have 1 and 1 here. So without looking into the actual definition of if and only if, I'll tell you this. This is good. This is good. These two are not good. Okay? And then we look at implication. Implication says good, good, not good, good. We look at implied by, good, not good, good, and good. So the zeros and ones that you see under A if and only if B, A implies B, and A is implied by B, is basically saying what can happen if I claim that A happens if and only if B. That means A and B can both be false, and they can both be true, but they cannot be different. That is what if and only if means. Is that okay? If I say A implies B, and I say that the implication itself is true, then you look at all the rows where the implication has a 1, and you say all of those things can happen, which in this case means A can be false. Oh, look at this. If A is false, doesn't matter what B is, the implication is automatically true. If you are in my CISP310 class, yes, this is deja vu because we talked about this already. Okay? When you look at A is implied by B, or B implies A, either way is fine, then the only time the implied by operation is false is the second one. It's when A is false and B is true. If I say A is implied by B as a statement is true, that means A and B can be the same, or A is true and then B is false. Now, in this discussion, we need A if and only if B. So that means there are 4 directions. Okay? There are 4 things we need to notice. If the borrow flag is a 1, then we know the value of x, unsigned value of x, is in fact less than the unsigned value of y. That's 1. If the borrow flag is a 0, then we know the unsigned value of x is not less than the unsigned value of y. Then somebody may ask, well, can we tell whether it's equal to or greater than? The answer is no, we cannot tell. Okay, we can only confirm it is not less than. Number 3, if you start with an unsigned value of x that is confirmed to be less than the unsigned value of y, the borrow flag is going to be a 1. And the last one, if you start with an unsigned value of x that is not less than the unsigned value of y, then we know the overall borrow is going to be 0. Okay, so if and only if is saying all those 4 things. Is that okay? All right. So I understand that sometimes this doesn't sound like, okay, I cannot really see the difference because they're about the same words, okay? If, only if and only if, they're very similar linguistically, but in terms of logic, they are very distinct, they're different, okay? Do you think these concepts are important in programming? I think the answer kind of can vary. It all depends on how good of a programmer you want to be. If you want to be a programmer, who is worth your salt, okay, and you can look up the idiom and find out why they use salt, these concepts are very important. Okay, in your head, in your mind, you have to keep asking yourself these questions. Why did text say if and only if? Is it different from if? Is it different from only if? How are they different? Why is if and only if applicable here? Those are the questions that I want you guys to kind of pop up in your head. If I have like a augmented reality application, I want to see question marks popping up on your head. When I mention something that's new, I want to see a lot of question marks popping up. Because that means you guys are actually asking the question internally, which is a good sign. If I mention something that I have never mentioned in class and I state, this is true, okay? I'm telling you this is true and there's no bubble coming up, then I would go like, well, as a professor, I have failed miserably. Okay, I'm not sure how many of you know what I'm talking about, but if you don't, it's okay. I have just failed miserably. Okay, so getting back to comparison. Okay, so I think we are now done with unsigned comparison. Just look at the borrow flag. Okay, the overall borrow for n-bit subtraction, which is we know as T of n, is the one thing that you need to look if you just want to confirm whether the minuend is less than the subtrahend. Are we good? Okay. So now we look at signed comparison. Okay, so we draw a big bar here, and now we look at signed comparison. Okay. So with signed comparison, things can be positive, or the values being represented can be positive or negative. Okay? And I'm pretty sure most of you still remember algebra enough to understand the following. Okay? Because all we want to do is to confirm whether the value of x is less than the value of y. I'm not going to use v of x and v of y anymore because that's just a lot of extra things. So when you see something like this, I'm looking at in this case, the signed value represented by x is less than the signed value represented by y. Are we good so far? Okay. Okay, so we can take y away from both sides, right? In algebra, in an inequality, if you take away the same amount from both sides, well, the inequality should still hold. So we say x minus y is less than, okay, I shouldn't skip that step. Is that okay? I just take y away from both sides. So the inequality still holds. Well, but another way to look at y minus y is it is 0. Are we good so far? Yes? So we look at this, and what do we call, okay, I just wrote it. Yeah, it's called a race condition. It's like, is my hand fast, is the signal going to my hand faster than going to my mouth? And in this case, it went to my hand a little bit faster than my mouth. So when I was about to ask the question, my hand has already answered the question for you. It's called a race condition. For those of you who want to become electrical or computer engineers, it's one of the worst things that can happen in a design. It's a race condition. So if many years later, like 20 years later, you end up with a project and you have a race condition, and then you just remember, oh yeah, Tech explained that when he was writing the answer faster than he was asking the question, I have just succeeded as a professor. This is how I define your success versus failure. Okay, so you look at this and go like, hey, we know how to do this, because if D is less than 0, what can tell me that D is less than 0? Looking from the signed perspective. There's a certain bit, yep. The sign bit, yeah. We know the sign bit is a 1 if and only if the value represented is less than 0. Okay? Now, I'll present another way to look at this, but right now we kind of know that. Do you guys remember the number wheel? Yes? Okay, so all the non-positive, all the negative values, they all have a 1 as the most significant bit. So the most significant bit is also known as the sign bit, because if the most significant bit is a 1, okay, the most significant bit is a 1 if and only if the signed value represented is negative. Yes? Okay? So now we look at this and we say, oh, okay, so D or x minus y is less than 0 if and only if the sign bit of D is a 1. Is that okay? I mean, because if D is less than 0, then it's going to have a sign bit of 1. So it seems like we have a winner, right? It seems like we can just look at the sign bit of the difference and use that by itself to tell us whether x is less than y signed. Yep?
Why would this be any different than just comparing the overall first digit, since that's typically the sign notation? It tells us whether or not it's negative.
Ask the question one more time.
Why don't we just compare the first?
What if they're the same? What if you're comparing two negative values? What if you're comparing two non-negative values? Right? Okay. So this looks good. Okay. So we'll go through a few examples to show the cases when this works. Okay. So let's look at 0 and 1. Okay. So that's pretty easy. So we look at 0 and 1, and we look at these as 4-bit numbers. Okay. We do the subtraction. 0 minus 1. Okay, so let me just do the long subtraction because I do want to make sure that you guys understand how to do this by hand. So this row here, the Q row, that's the exclusive OR between the X and the Y. When they are different, the exclusive OR is a 1. When they are the same, the exclusive OR is a 0. Are we good so far? Then we look at the T row. Okay, this is the take row. If we start with 0 because that's the least significant bit. This position here is a 1 if we have a borrow situation, either from this 0 minus 1 or this 1 minus this 0. Okay, is an OR. In this case, the first one gives us a borrow, so we have to put a 1 here. Is that okay? Then we look at this guy here. Now this guy is influenced by 0 minus 0 or 0 minus 1. If one of those two has a borrow, then we have a borrow here. Well, 0 minus 1 has a borrow, so we have a borrow here. we look at this position, and same thing, we look at 0 minus 0, okay, no borrow. 0 minus 1 has a borrow, put it here. Same thing over here. This is our overall borrow. This is T4 in the 4-bit subtraction. We have 0 minus 0, oops, 0 minus 0, no, oh, okay, take it back. This 0 minus this 0 has no borrow. This 0 minus 1 has a borrow, put the 1 here. Okay. Then we look at the D row, which is our difference, which is just the exclusive OR between the Q and the T. If they are different, we have a 1. If they are the same, we have a 0. Different, 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 different. Okay, that's our result. So because we are only caring about signed comparison at this point, we look at the overall borrow bit and go like, that is not applicable right now because we only want to look at things from the signed perspective. So we look at this and go like, look at this overall sign bit here. The sign bit is a 1, so the conclusion is 0 is less than 1. Okay. Is true. Okay, well, that's pretty easy. Let's look at another one. Okay, this time we have a negative value. So we have -1, which is represented by 1, 1, 1, 1. And we're going to compare that to, guess what? 0. Okay. I don't think we need to work this out too much. We should end up with an overall borrow of 0 and a difference of 1, 1, 1, 1. Okay? Or do you guys want me to go through the full subtraction? Okay, very good. Now we look at the overall borrow of 0 and go like, we're going to ignore that because this is not an unsigned comparison. This is a signed comparison. As a result, we just look at the sign bit of the difference, which is this one here. Okay? So this one is telling us that our minuend, which is representing -1, is in fact less than our subtrahend, which is representing 0, and this is true. Seems to work, right? So now we look at some other cases and go like, well, does this work in general? Okay, can we always tell whether the minuend is less than the subtrahend by looking at the sign bit? As it turns out, unfortunately, that is not the case. So I will give you an example when it doesn't work. So what doesn't work? Well, we got a 0, 1, 1, 1 representing 7. And then we have 1, 1, 1, 1 representing -1. Now, if you're wondering why 0, 1, 1, 1 is representing 7 and why 1, 1, 1, 1 is representing -1, you can kind of go back to the number wheel discussion because that's kind of where this comes from. So with this one, I think I'm going to go for the full subtraction just so that I can illustrate the whole process. Okay. So if they're the same, this is the Q row. If x and y are the same, we get a 0. If they're different, we get a 1. Okay, pretty easy. 0, 0, 0, 1. The borrow, is looking at two subtractions. There's no borrow here because 1 minus 1 does not have a borrow. 0 minus 0 does not have a borrow either. And there's no borrow here because, once again, we have 1 minus 1, 0 minus 0, neither has a borrow. And then we have a 0 here because we have 1 minus 1, 0 minus 0 again, no borrow. And then this time we have a borrow because 0 minus 1 does have a borrow. Is that okay? So this is how we work out the T row. And then the D row is the exclusive OR between the Q and the T. So we just say if they're different, it is a 1. If they are the same, it's a 0. Same, 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 different. Are we good so far? So this one, being the sign bit, this is telling us that 0, 1, 1, 1, which is 7, is less than 1, 1, 1, 1, which is representing -1, is true. Yes?
So because our number wheel doesn't support positive 8.
Exactly. Because once you choose that you're dealing with signed values, then you have just locked down the number wheel to go from -8 to positive 7. Those are the values they can represent. So this 1, 0, 0, 0 is actually representing negative 8. But we know that 7 minus negative 1 cannot be negative. That makes no sense, because if you subtract a negative quantity from a non-negative quantity, it should always be non-negative. But we have just crossed over that line because we ran out of values that we can represent using only 4 bits. And that's why it's called an overflow situation. So you can see that when we have an overflow situation, the sign bit cannot be relied on anymore. It will say the opposite of what it is supposed to be. Yes? Mm-hmm.
If overflow is the only issue with this method, can't you just make an extra gate to account for overflow?
We can detect overflow. Okay, so we'll talk about how we detect overflow. Okay, so this is one situation where we can have an overflow. There's one more. So we'll go ahead and look at that one more situation where we can have a overflow. So the other overflow is in the other direction. Okay, so we just started out with a case where we have a non-negative value minus a negative value. It should always be non-negative, but we somehow ended up with a quote-unquote negative value. That's one overflow. So the opposite is to start with a negative value minus a non-negative value, and then somehow we end up with a non-negative value. Okay? So we'll start with that. I mean, it's pretty easy to work it out. Okay? So we have 1, 0, 0, 1. And what value do you think this is representing? You guys can look up the number wheel. Negative 7. Very good. Okay, so this is negative 7. And then we have 0, 0, 1, 0, which is representing 2. Go through the subtraction. So this is the Q row. This is the T row. Okay, there's no borrow here. There's a borrow here. There's a borrow here. There's no borrow here. And then we have the D row, which is 1, 1, 1, and then the 0 over here. So this 0 is telling us what? It's telling us that negative 7 is less than 2 is false. Once again, we say, what the hash? And we can make it a SHA2 hash too. So, once again, we just ran out of values because negative 7 minus 2 is negative 9. But the most negative value you can represent using only 4 bits is negative 8. We just ran out of representation on the number wheel. So once again, we have an overflow situation. Okay? So what do you notice about the overflow situation? There's one common thread to all this. The sign of the difference does not make sense. Okay? Okay, so we look at all the possible situations and we say, okay, under what situations does the sign of the difference make sense, and under what situation when the sign of the difference does not make sense? Okay? So let me label these things. So we'll look at only these bits, okay? Different colors. Okay, let me fix the color here. Okay, we look at these bits only. So we only look at the sign bit of the minuend, subtrahend, and the difference. Okay? I certainly hope those terms are now starting to get a little bit more familiar, even though we haven't talked about it for 4 days. Right? So this is our MS, this is our SS, and this is our DS. And those notations should be somewhat familiar by now. Yes? I understand on last Thursday they can look a little bit confusing, but I think after today, they should not be confusing anymore. All right. So with 3 bits, we have 8 possible cases. So we look at MS, SS, DS, and then we make a table out of this. So we say 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay. So I have just enumerated all 8 possible cases of how you can combine zeros and ones if you just look at the most significant bit or the sign bit of the minuend, subtrahend, and the difference. Okay? So the question now is, does this make sense? Okay? So let's look at the first row. The first row says you start with a non-negative value, you subtract a non-negative value from that, and you end up with a non-negative value. Can that happen? Let's check. 0 minus 0 is 0. They all have a sign bit of 0. Seems to be okay, right? So it does make sense. The next one is you start with a non-negative value, you subtract a non-negative value from it, but you end up with a negative value. Can that happen? Let's see. 0, 0, 0, 0, which is representing 0, minus 0, 0, 0, 1, which is representing 1, is negative 1. It can happen. Is that okay? So we are just filling up all these rows of what makes sense and what does not make sense. Okay? So the next row says, I'm just going to go through one more and then I'll just fill in the row, the column. So the next row says, if you start with a non-negative value, you subtract a negative value from it, and you end up with a non-negative value. Can that happen? It happens. It should happen every single time. Okay? So yes, in fact, this makes sense. But wait, if that makes sense and it should happen in every single case, that means this does not make sense. It is not possible. Exactly. And this one is not possible either. Because this one says we start with a negative value, we subtract a non-negative value from it, and then somehow we end up with a non-negative value. That doesn't make sense. Okay? And then all the other ones make sense. Okay, 1, 1, and 1. So the cases where it makes sense, there's no overflow because it is okay. We have enough bits to represent the difference. Okay? So when you look at the overflow or the overflow flag, it really is just the negation of what makes sense. Because when it does make sense, we don't have an overflow. When it does not make sense, it is because we have an overflow. Is that okay? Okay? So we just say, oh, okay, we just flip all the bits. 0, 0, 0, 1, 1, 0, 0, 0. Okay? So now what we want to do is to say, well, can we define the overflow flag as some kind of Boolean expression involving the minuend sign, the subtrahend sign, and the difference sign? What do you think? Exactly. Yes. So sometimes it helps to do the assignment first, and then when I explain it, it just click, 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 right? Okay. So we look at this and go like, well, we just need these 2 rows, okay, to give us a 1. So that means, hey, if I negate ms and then AND it with the non-negative version of ss and the non-negative version of ds, that will account for this thing here. Okay? So that looks like the negation of ms. So it turns a 0 into a 1. The non-negative version of ss and the non-negative version of ds, those were 1s already. They don't need to be negated. So when we AND these 3 things together, it will give me a 1, but only for this row. There's a separate row that we need to turn into a 1, which is this one over here. Exactly. It's the opposite. ms is non-negated, ss is negated, ds is also negated. So if you want to know the priority of operations, I can put in extra parentheses. But this is how the overflow flag is computed. I mean, it's great if we can look at it from the perspective of whether it makes sense or not. But I don't have a magical gate that can say, does this make sense? Okay? So, yes. Or intuition, right? But I cannot implement it, okay? Because you cannot manufacture computers using your brain. Pretty sure. So we need logic gates to get the same thing done, and that's why we derive the logical expression. And that really is the whole lab on last Thursday, which is not due until this Thursday. So if you're not satisfied with your answers last Thursday, now you get everything connected, you want to redo it, you can go ahead. So do we have any questions at this point about signed comparison versus unsigned comparison? There's a little bit more to this. We have to kind of tie up some loose ends, but this is the most important part of signed comparison. Is why do we have an overflow? Why can't we trust the sign bit alone? Yep.
Can we use what we discussed earlier as a means to express the less than comparison, so long as it doesn't have an overflow, and if it does, then we
Okay, very good. Okay, so you are definitely thinking ahead, which is good. Okay, so we have the sign flag, we have the overflow flag, right? The sign flag can be a 0. The sign flag can be a 1. While the sign flag is a 0, the overflow can be a 0 or 1. When the sign flag is a 1, the overflow can be a 0 or 1. Okay? So we want to look at the combination now between the sign flag and the overflow flag, and then we ask, is x less than y? Okay? Right? Okay, so we look at this table, and we basically say, if the overflow is a 1, that means the sign flag is telling you the opposite of what it is supposed to be. Is that okay? So the sign flag normally, if there's no overflow situation, the sign flag alone is enough to tell us whether x is less than y or not. The sign flag is a 1 if and only if x is less than y signed, right? Okay, in this case, okay, there's no problem because overflow says, yep, everything is good. And then sign flag says, no, x is not less than y. Well, we can trust the sign flag in this case because there's no overflow. So x is less than y is indeed false in this case. Next row. The next row has a situation because the overflow flag is a 1, which is basically telling us, oh, the sign flag is going to report the wrong answer in this case because there's an overflow situation. Now, normally, a wrong answer is a wrong answer. You cannot derive the right answer when somebody gives you the wrong answer. But you can when it's Boolean. Because with Boolean, how many ways can you be wrong? One way. Okay? So on this row, the overflow flag says, okay, the sign flag is telling you the wrong thing. The sign flag says, nope, x is not less than y, but that's wrong. What is the conclusion? X is less than y. Very good. Okay. I think we're getting the hang of this. The next row says, there's no overflow, okay, so we can trust the sign flag. The sign flag says, yep, x is less than y. Well, we can trust the sign flag in this case because there's no overflow. So, sorry? Half the time it is. So the last row says we have an overflow situation. Knowing that there's an overflow situation, the sign flag says, yeah, x is less than y. But we know the sign flag is wrong in this case because there's an overflow situation. So the answer is no. That's right. So we look at this and go like, is there a better way to explain this or to work this out without having to mention, is there an overflow situation, and if there is, the sign flag is wrong, blah, 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 blah. You look at this as a truth table. In other words, you hide the top label and you just look at the truth table itself. Does it remind you of something? Exclusive OR, okay? The R function, right? How Q relates to X and Y, how the sum relates to Q and K, how the difference relates to Q and T. It's exclusive OR. So this entire row, or this column, is signed, exclusive, or with overflow. Is that okay? And in this class, I give it a particular name. I call it L. So why do you think I call it L? What does L stand for? Less than, very good. So I call this the L flag. So are we good so far? Let me just enumerate all the flags that we have introduced up to this point. We got the borrow flag, which is the last or the most significant borrow of a subtraction. It's the one that is not represented as a part of the difference. We have the sign flag, which is the sign flag of the difference. Okay, when you just see S, it is the sign flag of the difference. Okay, which is also known as the most significant bit of the difference. Same thing. We have the O flag, which is a flag that says, well, did we just run out of representations on the number wheel, and there's no way to represent the actual value of the difference. And then we have the L flag, which is derived from the sign flag, exclusive or with the overflow flag, because most of the time, we don't want to just look at the sign flag, and we don't want to just look at the overflow flag. We really just want to know, is X less than Y? So we look at the L flag for that conclusion and go like, okay, if it is less than, go here. If not, go somewhere else. So are we okay so far? Yes? Do you guys remember when I asked you, should we look at this as a signed value? Should we look at this as an unsigned value? And my answer was, why do you care? Do you remember that? Yes? Okay. So the only time you care is you have to determine, should I use this flag to decide whether to go left or right, or should I use this flag to decide whether I should go left or right? Okay? If you know that the values that you are dealing with are signed, use the L flag. Only look at the L flag. Now the B flag is around, but ignore it. Okay? On the other hand, if you know the values that you're dealing with, they're all unsigned, then ignore the L flag. Just look at the B flag if you need to make a decision. That is the whole point. So you care only when you need to make a decision based on whether X is less than Y. When you do care, you have to choose. If it is unsigned, look at the borrow flag. If it is signed, look at the L flag. That's going to be important, okay? For the rest of the semester. Well, I shouldn't say from here on, but it will come back later, okay? This is all going to be coming back later when we talk about how do we implement C code in assembly code. So this is all really important stuff, but we are going to shelve it for a little bit of time because we got some other stuff to talk about. So are we doing okay here? Yes? Okay. And all of these are basically byproducts of subtraction. So subtraction is super important, not only because we sometimes care about the actual difference, but also because we need to compare. The very same mechanism that we use for subtraction is the mechanism that we use to compare. So is that okay? All right. So for those of you who are a little bit ambitious or just want to do this, you can turn your 3x3 carry look-ahead adder into a adder/subtractor. Then you can split the bits out of X, Y, and the difference, and add this additional logic here to also output the overflow flag, to also output the sign flag, and also to output the L flag. Okay, it's just a little exercise. If you want to do it, it's not going to be graded, but if you want to go ahead and do it, I think it's going to be helpful because one, it helps to gel what we have talked about today because you're doing in LogicSim and you can test it and you can get a better understanding of how it works. And two, it just gives you a little bit more opportunity to use LogicSim, because LogicSim is going to be the tool that we'll be using for the rest of the entire semester. So the more you're used to it, the faster you can get additional assignments done. So I think it cannot be a bad thing. All right, so do we have any other questions regarding comparison? We got about 3 minutes left. I do have something to start, okay? Okay, so if there are no questions about this, I'm going to at least mention what we'll be talking about on Thursday and what you can do to prepare for that particular topic. All right. So there's no new lab tonight, okay, because we didn't quite get to floating point number representation. So this is what we'll be starting on Thursday, okay? Now, this one, I can show you just a little bit of this note here. You probably want to brush up on your math stuff when it comes to log, exponent, try to figure out how many bits you need to represent a particular value, that sort of stuff, okay? Because floating point numbers have to do with breaking up a value into two main parts, the mantissa and the exponent. Okay, so let me ask you this question. Does everybody in this class understand what is scientific notation? At least you know how to enter a value using the scientific notation on a calculator. So are we good on that? Okay. It's kind of the same thing, but except it's binary. In other words, your mantissa they're all zeros and ones, and it's always 1 point blah, 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 okay? And then your exponent is expressing 1 point blah, 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 blah as a binary number times 2 to the power of what? So instead of 10 to the power of something, it is now 2 to the power of something. But the idea is the same. You have the mantissa, then you have the exponent to specify the order of magnitude. Yep.
The mantissa is just whatever the exponent is.
Right. On a normal calculator, in base 10, if you want to say 1.23 times 10 to the power of 40, okay? This is called the mantissa, and this is called the exponent. This is actually a legitimate way to enter 1.23 times 10 to the power of 40 in C or C++, okay? That's how it is done using the scientific notation. But in binary, this can only have zeros and ones, okay? And then this one is no longer a power of 10, it is now a power of 2. But otherwise, it's the same concept. So on Thursday, the lab on Thursday is going to involve exponents, logs, order of magnitude, and that sort of stuff. So you might want to kind of brush up on those topics if you're not familiar with those topics at this point. So there's no new lab tonight. If you are working on the lab that is due on Thursday, I'll be in the lab to answer questions. If not, if there's nothing else to do. Yep. No. There's no activity, so you don't have to sign in for row sheet purposes. Is that the same question? Yeah. Okay. Thank you.